Hello and welcome to our lab. My name is Christoph and today I would like to talk to you about our work at BAM on how AI might help to develop more sustainable concretes. Let's kick off with some rather interesting facts about concrete. It may surprise you to hear that concrete is the most consumed material produced by man at 30 billion tons per year. That's almost 4 tons for each person per year. The only material we use more of is water. But there is an elephant in the room. And the elephant is that, unlike water, concrete production is a real threat to our climate. 8% of man-made CO2 emissions come from cement production alone. If cement was a country, it would be the third largest carbon emitter, after China and the United States. Many researchers are working to rethink cement and to ecologically redesign cement products. Alternative concretes could turn the tide, but their development is very challenging. So, how are we contributing to this with AI? Are we building some kind of AI superbrain somewhere in BAM that can predict how to make concrete more sustainable in the future? Well, kind of, but it's probably not what you expect. Let's see how this really works. You can think of materials research a little bit like baking a cake. Of course, instead of cake, we make concrete, but just like the cake, it consists of various ingredients and processing steps. Concrete recipes are constantly further developed to improve the quality of the product and, above all, to reduce its carbon footprint. This is usually done through work that builds on each other. Each contribution raises new research questions that will be explored in the next study. But there are some major challenges, some of which are unique to concrete. One problem, for instance, is the complexity of the materials. The days when concrete consisted only of cement, water and aggregates are long gone. Today's formulation contains many more ingredients. Cement, for instance, is being replaced in part because it contributes to the material's high carbon emissions. Unfortunately, it is also responsible for the strength of the concrete. So, replacing it is tricky and requires a balanced mix of additives and chemicals. This makes the list of ingredients longer, which in turn leads to more possible combinations. The ratio is exponential, which means that even a few additional ingredients will cause the number of possible recipes to explode. In the laboratory, perhaps 10 to a maximum of 100 materials can be investigated in reasonable time. But since there are much more possible variants, further development has become a lot more difficult. Where to start? Further development has really become like looking for a needle in the haystack. But even in those cases where the theoretical understanding of concrete systems is comprehensive, the sustainable ingredients can vary greatly depending on their origin and react accordingly different. The inconsistencies of raw materials adds to the complexity of the material and can lead to significant quality variations without additional adaptation of the formulations in the lab. This makes the adaptation of more sustainable concretes challenging in practice. So, concrete can take a long time to develop, but it has been shown that the world can change in an instant. As a result, certain material systems have become virtually unfeasible due to higher energy costs, unstable supply chains, and the unavailability of byproducts from changing industries. A rapidly changing environment and a complex material to develop, are a significant challenge. So, how can AI help with this? Well, it turns out that AI is really good at processing different, sometimes very complex information collaboratively. So, instead of exploring material properties like strength, durability, and workability isolated in the lab, AI enables naturally to incorporate socioeconomic factors like sustainability, costs, resources, and supply chains to answer the most relevant scientific questions. AI does this in a highly efficient way, and here's how. For starters, digital material recipes and some few validation data from the lab are required. Then a machine learning model comes into play. It models the relationship between the recipes and the lab data with mathematical functions. Once these functions are fitted to the data, they can be applied to new material recipes. The learned relationships from the previous lab tests now allow it to predict the outcome of the new recipes with some margin of error. The beauty of this is that it can happen very quickly. Thousands of new materials can be predicted in a second, where laboratory tests would have taken decades. The availability of so many potential outcomes is proving very useful to cope with the enormous complexity of sustainable materials. But how do the socioeconomic factors come into play? Let's see on the next slide. To this end, there is the concept of utility. Let me explain. Shown here are three materials marked as stars. The coordinates of these materials come from the predicted performance in the lab on the y-axis and the socioeconomic impact on the x-axis. If both the predicted laboratory results and the factors such as CO2 footprint are good, the material is found to be of high utility. If both are bad, it has a low utility. The third case is interesting. Although the material properties are promising, it seems to perform rather poorly from the perspective of socioeconomic factors. Such a material may initially appear very promising in the laboratory, although it is ultimately useless when compared to the option on the right. By taking a holistic view in the AI-based approach, it is easy to make the right prioritization before spending weeks and months in the lab. Let's recap. Complex research questions, such as the variation of many ingredients in production steps, can be easily represented with materials recipes. But because the real-world performance of these recipes is unknown, it is difficult to select the right one ahead. Also, socioeconomic factors can play a crucial role for the selection, but these can often be easily derived from the recipes. With some validation data from the lab, the expected utility of materials can be predicted via AI for a sea of possible variants. Experiments with the highest utility potentially lead to the desired result in the laboratory most quickly. However, since the AI does not necessarily have all the relevant information at the beginning, it is advisable to iteratively collect new validation data. With this data, the AI model is adjusted and new prioritization proposals are made. It is now very likely that a suitable material will be found after only a few iterations. Note that out of the vast number of possible recipes, only a fraction has been validated in the lab. This makes this approach highly efficient. With AI optimization, the properties of the materials are systematically enhanced in each round. This can lead to finding ideal materials after only a few development cycles. So let's see how this works in practice. We have developed an app called Slammed, you see it here on this slide. It can be used to perform AI-based optimization of concrete and cement formulations. It is available to everyone for free on our GitHub repo and can be installed in a few simple steps. The link is shown here on this slide and also in the description below this video. A web version will follow later this year. SLAMP consists of two main parts, a digital lab and the AI optimization. What is the idea of the digital lab? Here we create all the items we need to make digital material formulations. This basically means to filling a shelf with all the ingredients and processes to make the material. This forms the basis for the material recipes in the next step. For each material and process there is a digital twin that allows the most detailed information to be captured. Factors such as carbon footprint, costs, etc. can also be entered here. In practice, it looks like this. The digital twins are created via simple forms for each material type and process. The forms contain the fields for the costs and material properties. These forms can also be easily extended. After adding some materials and processes, a filled-up shelf looks like this. All these items are now available for the next step. Here we can create the recipes by combining different ingredients and processing steps. The digital twins are merged and each recipe is enriched with the detailed information of its ingredients. Instead of defining each recipe individually, an entire batch is defined directly by setting its boundaries. This is done simply by specifying the minimum and maximum quantity of each ingredient. After only a few mouse clicks, large tables with many recipes are then created fully automatically. With some lab data at hand, the optimization now follows. This slide shows about 200 small dots. Each dot represents a material recipe. The color indicates the expected utility of the recipe. The more yellow, the more useful. The arrangement of the dots is similar to the slide we saw at the beginning. Materials that are made in a similar way are next to each other. What is interesting now is that we can see right away that there appear to be three clusters of materials, each divided into two halves. This is in fact a consequence of the experimental configuration. It contains three different precursors, each of which is processed in two different ways. Therefore, we see three clusters with two halves. The reason why there are so many more points is that different weight ratios of the ingredients are additionally investigated. Since all colors are in all clusters, it is clear that all design decisions have a decisive influence on the outcome of the materials. There appears to be no trivial solution that we could have seen coming a long time ago. Rather, it is very complex. However, with this representation, it is a snap to select the most promising candidate. Again, all this is possible with minimal laboratory effort. For this example, only 10 out of the 200 samples were validated. They are shown here as the small black crosses. The great thing about this computer-based approach is that we can redefine the utility at any given time. This makes it possible to custom tailor the best material for almost any application and boundary conditions. Currently, the utility is calculated for a material that should have at least 45 megapascal strength, while having the lowest possible CO2 footprint. We change the target to find the maximum strength, the utility is recalculated. The colors change and the selection is again super simple. Here, a recipe based on precursor 1 seems to perform best. So, to conclude, have we developed an AI superbrain? Well, sort of, But instead of a big data center, you can think of it more like an app that can be operated by any lab technician. It does not require massive amounts of data either. The opposite is true, which may come as a surprise. Unfortunately, this AI does not automatically solve every question in materials research. Rather, it is a new tool that builds on the highly specialized questions of the classic cement lab. Instead of exploring the influence of a specific cement constituent in detail or precisely understanding chemical reactions, the approach enables us to answer a new set of more general questions. How can we ecologically redesign our proven formulations without compromising quality or exploding costs? How can we respond more flexibly to fluctuating market situations? Can we fine-tune our materials to deliver exceptional performance? And finally, can we autonomously develop more sustainable building materials without human interaction by using robots to perform and adapt standardized laboratory tests? These are certainly very interesting questions, and we hope to give some answers with our app. If you have more questions, feel free to ask them in the comments. This slide shows some more resources. Feel free to follow us on Twitter or LinkedIn to stay up to date. Finally, I would like to thank our partners, the Department of Building Chemistry and Materials at TU-Berlin, for encouraging us to pursue this topic and for answering our many questions, and the company Iteratec, with whom we developed the app and who took the app's laboratory capabilities to the next level. With this, I want to thank you for your interest. See you soon. Bye.